Let's talk about order of magnitude, sometimes called Big O. This is basically a set of values that help us understand how many steps it will take any particular algorithm to process a certain number of pieces of data. There are essentially 5 levels. And so we'll talk about each one of these 5 levels. And the values of n that we're using are these right here, 2 through 2000. Now let's talk about the first one, O of 1. O of 1 basically means that regardless of the size of the data, it will only take one step to process it. So an algorithm that would take only one step regardless of the size of the data might be finding the first element of the array. If it's a contiguous array in memory, it's all side by side, that's just a simple mathematic question. Same thing with the last element in the array. It will take one step to do that process. Or finding the length of the array, one step, because it's a math formula. Now, an O of n process will take exactly the same number of steps as there are pieces of data. So if it's 2 pieces of data in the data set, 2 steps. 3 pieces, 3 steps, and so on. So this is called a linear process. And a typical example of a linear process is like outputting all of the elements in the array. So if there were 2,000 elements in your array, it's going to take you 2,000 steps to output each one of those. Now, an n-squared algorithm will take n-squared steps to process the data. So if n is 2, it's going to take 4 steps to do it. If n is 3, it will take 9 steps. 4 will be 16 steps. Stop the video and figure out the rest of these. Okay, let's see how you did. 6 squared is going to be 36. 10 squared is 100. 50 squared is 2,500. 100 squared is going to be 10,000. 1,000 squared will be 1,000,000. And then 2,000 squared will be 4,000,000. Now let's talk about this column for a second, the first mystery column. This is called log n. And this is where it would be helpful to look at your powers of 2 table that we did in the last video. A log is simply an exponent. That's all it is. A log is an exponent. And so what we want to know is, what is the exponent that we used to get this value? Well, the power of 2 exponent to get 2 is simply 1. So the log of 2, base 2, is 1. If we skip to the 4, the log, the exponent, using 2 as a base to get 4, is 2. Now, if it doesn't exactly fit, then you just go to the next number in the sequence. For example, 3 is not in our powers of 2 table, so what is just past 3? Well, it's 4. So we're going to use the same log value as 4. 6 isn't exactly on the powers of 2 table either, but the value just past the 6 is the 8. And so 3 is the log value for the 8. Stop for a minute and see if you can figure out these next 3. All right, let's see how you did. 10, not in the powers of 2 table, but the next value after 10 is 16. And so 4 is the log for 10. For 50, it's 6, because 64 is the value that you use. That's the next one in the table. 100 would use the value 128, which is log 7. 1,000 is going to be 10 as the exponent, and 2,000 would be 11 as the exponent. And so this type of process takes this many steps in order to process this many pieces of data. That's pretty darn good if you have 2,000 pieces of data and it only takes you 11 steps to process it. That's very efficient. And a typical example of that is a binary search. And if you've seen the dictionary search process, the demonstration, then you'll understand what I'm talking about. If you haven't, you need to look at that video and it will make more sense to you. Now, this next one is n log n. And this is easy to calculate because it's just simply the product of these two. So 1 times 2 is 2, 2 times 3 is 6, and so forth and so on. This is a typical process that some of the more advanced sorts will be rated at. For example, the merge and the quicksort both have an efficiency of n log n. Now, if you compare that to n squared, it is much, much better, especially as n gets large. If n is 2,000, it's only going to take 22,000 steps to sort instead of 4 million steps. That's significantly smaller. And so that's the idea, is you have 5 different levels of efficiency that can be used to rate different algorithms. And so if you have a fairly clear understanding of what this is, then you'll be in good shape. You don't have to memorize the table. Just understand the processes behind it, and you'll be able to understand how to choose what the rating is for a particular algorithm.